Okay, so let me first go to that. Okay, so before we start, any questions from the previous lecture, previous week? No? Okay, there is a little bit change in today's format of slides. Actually, I was attending there is this session from Teaching Academy in an MSU, and their job is, or their purpose is to help us to improve our teaching. So they suggested that ideally an instructor should be consuming or spending 2 hours for preparation if you want to deliver a lecture of 1 hour. And at most, it should be the ratio of 4:1, 4 hour preparation for a lecture of 1 hour. In my case, it was like 7 to 8 hours, 7 to 8 hours for one lecture, which means it is too high. And actually, they were right because, as an assistant professor, my responsibility is not only teaching, but also research and services. So if I'm spending like 7 to 8 hours for one lecture, it means I'm spending my 2 days completely only for preparing lecture, doing nothing else, which is like being so low on performance in terms of like research. So in this lectures, from actually starting from this lecture, what I'm going to do is that previously I was modifying the slides according to my own style, what I want to follow, what I want to convey. And I was putting all that material in the slides. So it was taking more time for me. So now, from now on, what I'm going to do is that I'm going to use the slides as it is from some other professors, but I'm not going to modifying them, but I will make sure that I discuss all those points which I want to discuss without putting them in the textual or graphical form in the slides. Maybe I can do drawing on the boards. That will be more like, that is less time consuming, but it will achieve the same target, which is like conveying the message or conveying the idea. Okay, so what does it mean? It means that in the lecture slides, maybe there will be some stuff which is not in the lecture slides, but it is covered in the lecture. So you either need to watch the video recording if you later want to like refer to it, watch the video recording or attend the lecture. Everything maybe will not be in slides. Okay. Clear? Okay. So, okay, last time we discussed that what we were talking about. We were talking about like, okay, now we have multiple processes, let's say thread, doesn't matter. And we want to increase the utilization of CPU. So we want to select one of those candidate ready processes for scheduling. Then what should be the criteria for selecting them? And also we said, okay, then there can be different criteria and there will be different scheduling algorithm for that. But then we will measure or we will evaluate those scheduling algorithm using different performance parameters. Like for example, CPU utilization, throughput, waiting time, turnaround time, response time, and so on. Okay. So in today's lecture, we are going to discuss those scheduling algorithms. And then we will see how they differ from each other. Maybe one of them is better in providing the lower waiting time, but then maybe worse in providing the lower turnaround time. And another algorithm maybe is better at providing lower turnaround time, but higher waiting time and so on. Okay, so actually, what I want to do is that I will go through these slides first after discussing them on the board. Okay. So let's say that you are in a situation where you have multiple ready processes already. Let's say I will use the word of process instead of saying that. You have multiple ready processes and you want to schedule them. And you want to pick one of them, right? Because we are assuming we have a single core. So we can execute only one process at a time. So if I ask you, let's say I have process P1, P2, P3, and for them, arrival time, the time when they become ready, is let's say all of them become ready at time 0. And burst time is the time how long it will take for them to complete their execution. Let's say it takes 10, it takes 5, it takes 15. Okay. So, and now if I ask you that, let's say you are the scheduler, you are performing the job of the scheduler, and we have a single core, so we need to select one of them. What will be your criteria? What will be your algorithm? Think about it. For a couple of, not couple of seconds, but let's say 10, 15, 20 seconds. Think about some algorithm which you can use to select one of those ready processes and schedule them. Okay, so anyone who has some idea, some criteria to pick up one of those ready algorithms, ready processes. So one thing they told us in the Teaching Academy session is that don't voluntarily ask the question. So maybe, can you give some idea? Do you have any idea about which of these should I select to schedule the code?
You can start with the shortest first time.
Okay. So he thinks let's start with the shortest first time. So here we have, yes, we can use that like as a criteria. So which means that basically which one of all of them became available already at the same time, 0, 0, 0, right? At the start of the time. And this one has the shortest one. The next shortest is 10, and that's the shortest is 15, right? So how can we schedule them? Let's say I draw this timeline. So the time is starting from 0 and it is increasing in this direction. So at 0, all of them are ready, right? So, but I will pick the one which is with the shortest time. So I'm picking this one, which is process 2. Let me change their names because A, B, and C, because it's a little bit more easier to write it. Okay, so I'm scheduling B, right? And then it takes 5 minutes, so it will be completed at time unit 5, right? So now it means that since I'm done with it, so now I need to again make a scheduling decision, right? So this one is done. Now between the remaining two, which one has the shortest time? This one, right? So I'm going to schedule this one on the for execution. And how long will it take? So it has the bus time of 10. So 5 plus 10, 15. So A is scheduled. And then this is also completed. And then we have left with only one candidate, right? So it has execution time of 15, so it will get completed at 30, and we have C here, right? So this is like the one algorithm which you can use to schedule the execution of the processes. But what is wrong with this? Let's say not wrong, but what is the requirement we need to fulfill in order to use this algorithm? What we need to know? Yes.
We need to know the shortest one, or the shortest time.
We need to what?
Know the process that takes the least time.
Yeah, that's fine. So, I mean, that is our criteria to make the decision. But we need to know in order to make the decision that what is the burst time of each process, right? So how long? But the issue is that we cannot know the burst time of each process in advance until you execute it actually on the CPU. You cannot know. There is no way that you can know how long it will take. Okay. So this is one issue that we need to know the or actually maybe if we cannot know, then we can estimate, right? Estimate the burst time for each process. So we need a mechanism or we need some algorithm, some way to find the burst time of each process. One thing. Second, okay, I will come to that second part later. So the issue is that we cannot exactly know the burst time for this. So what we can do is that we can use some mechanism to estimate this one, this burst time, and then based on that estimation, we can make the decision. Now this estimation is definitely not perfect, right? So how they estimate, the mechanism for estimating the burst time is that we can use the history of that process. That in past, how long it took for a particular process to complete its execution. How long was the burst time for that particular process? Okay. So this is one option, that this is one criteria which I can use. In my slide order, this scheduling algorithm was not the first one, so I am skipping quickly to the slides where we have covered this one. Okay. Shortest job first. So what we do is that we associate, so since now you have some idea, so I can go over these slides rather quickly. So what we can do is that we can associate with each process the length of the next CPU burst, right? And then use these lengths to schedule the process with the shortest time. Same thing which we have done on the board, right? Shortest job first is optimal in the sense that it gives the minimum average time. Actually, here we are trying to compare it with other algorithm, but I mean, I can come back later to it, that point of comparison. But it is provably gives the optimum waiting time as compared to all other algorithms. But the issue with this is that we need to know the length of the next CPU request and the length of next CPU burst time for each process, right? Which is not easy to know. So here is an example. I have already done an example, but let's say I can also walk you through this example of the shortest job first. Let's say you have 4 processes, P1, 2, 3, and 4. They all arrive at the time 0, and we are assuming, we know that their burst time in advance, 6, 8, 7, and 3. So the scheduling chart, which you will draw, will look like something like this, because at time 0, you need to make the decision that which one is the smallest one. So the smallest in the sense of burst time. So it is the process with time 3, process 4. So you schedule first it, and once it is completed, you need to again make a decision. So at time 3, you again look which one of the remaining 3 has the shortest time. So it is the one with 6, which is process P1. So you schedule this one, it takes 3 time units, and it gets completed at 9. Again, you make a scheduling decision and select between the remaining 2, which is 8 and 7. So the smallest one is 7, which is P3. You schedule it, it takes 7 seconds, 7 time units, let's say. Completes at 16, and then you have only one candidate. Okay. So what is the average waiting time in this, in this scenario, if you use the shortest job first? So the average waiting time, if you sum the waiting time of all the processes. So P4 waits for 0 time seconds, right? As soon as it arrives, it gets scheduled. So there is no waiting time involved. P1 waits for 3 time units, P3 waits for 9 time units, and P2 waits for 16. So you sum all of the average. So the average waiting time is 7 milliseconds or 7 time units. Okay. Okay. So as I said that we can only estimate, we cannot know in advance the exact CPU bus time of each process. We can only estimate the length. And we can do this by using the length of the previous CPU. For each process, what we do is that we use its history, that when last time it was scheduled, how long it took for it to complete. So this can be done using the length of the previous CPU burst for a given process, and then we use the exponential averaging of the previous burst lengths. I will take you back to this slide or this figure later on, but let's first move to the next slide and find out how we can estimate. Let's say that you have some particular process and the Tn, it denotes the length of the nth CPU bus, which basically means that what is nth CPU bus? Like, let's say that you know that a typical process, its lifetime or its execution time can be consisted of multiple CPU bursts and IO bursts, right? So if you remember from one of the previous slides, it could be like you spend some time here in CPU burst or CPU execution, and then you spend some time here for IO, and or maybe interrupt or something, and then again you do some computation. Maybe I don't know how long it is. Let's say here it was, I'm just making up 10 milliseconds. Here it is 20 milliseconds. Here let's say it's take 15 milliseconds. Again you have some IO burst and again some CPU burst. Here let's say I'm saying 5 milliseconds, right? So this is burst, CPU burst 0. This is CPU burst 1. This is CPU burst 2 and so on. Okay. So this is what we are saying here. The let Tn denotes the length of the nth CPU burst of a given process. So this is the actual length. When by Tn we mean that actually how long it took in the past. Like let's say now, let's say that the time has progressed until this time point. Okay. So this was T0, like this was T0, this was T1, this was T2, and the next we want to get is the next will be the burst 3, right? So for burst 3, again, we will have two different things. One, the actual time it will take, which we are indicating by T, and the estimation, which we are going to indicate by ta, symbol ta, okay? So let ta n plus 1 denote the predicted value for the next CPU. So we are actually, what we are trying to say is that here, for this burst 3, we want to predict the value, and that will be 0, 1, 2, so this was 0, 1, 2, and 3, right? So this will be tau 3, right? So we want to predict this value. Okay, so assume that the first CPU burst is burst 0, which I have shown there. And let's say its length, the actual time it took was T0. Here, let's say, and I think in our case is 10 milliseconds, if I remember correctly. Okay. And ta n denotes the previous estimate before Tn. So now we want to estimate ta 3, which is for this burst, but we also have ta 2, which is, let's say, the estimated value which we use here for bus number 2, 0, 1, 2. I'm talking in terms of index starting from 0. For that, what we can do is that we can use this equation where alpha is a constant or a weight, and its value ranges from 0 to 1. You can change it, but its value ranges from 0 to 1. So here what we are saying is that the estimated value for the next burst, n plus 1, is weighted sum of the actual execution time of the previous burst plus weighted sum of, plus you multiply with weight, the estimated burst of the previous burst, the estimated value. So basically we are saying here is that ta 3 is equal to alpha T2 plus 1 minus alpha and ta T2. Okay. Sorry for that writing. So here what we are saying is that we are doing the weighted sum. So basically we are predicting our next bus time based on the previous actual actual time for the previous bus plus estimated value for the previous bus. Any questions there? Yeah, go ahead.
Would alpha be given to us on the div, or do we just like assign it some arbitrary value between 0?
I mean, for the purpose of exam, you will be given, but or maybe you will be asked, okay, assume these two values and compare the performance. I compare the scheduling algorithm using these two different values of alpha, right? But in real life, what you can do is, depending upon your multiple factors, maybe you can experiment and you can see which one of which alpha value is optimal in a given application. Okay, maybe it can make a good project. I don't know. Maybe I can think about it. Okay. So in this previous equation, if you put alpha equal to 0, so it basically what you are saying is that your next predicted value, or next predicted estimate will be same as the last predicted value of predicted estimate. So that basically what you are saying is that recent history of the actual bus value doesn't matter, which was t. So you are saying that we don't count it. We only predict the next burst based on the previous burst. So which you are basically saying is constant, right? And if alpha is equal to 1, then you are saying that we base our estimation only on the previous actual burst time, not counting or not factoring in the value of the previous predicted burst time. Okay. And we can set alpha between 0 and 1, for example, 0.5. So typical value is 0.5, which means you give equal importance or equal weightage to both the previous actual burst time and the previous predicted burst time. So here is an example. Let's say task 0 is 10 milliseconds. Task 0 is basically means that when at the start, when the first time the process becomes ready, so at that time, what is your initial estimated burst time? You can put it as some constant. Let's say in this example, we are setting task 0 equal to 10 milliseconds. And then let's say that we have scheduled the process for four bursts, CPU bursts, T0, T1, T2, T3, basically, which means that when you consider this process in here, so you have four CPU bursts, CPU execution here, then here, and another one. So for 4 bursts, you have already executed it. And now then for the next 5th burst, you are going to predict the execution time. Okay. So for the first, the actual time was 8 milliseconds. Task 0 was 10 milliseconds. Actually, not first bus, second bus, because the index is starting with 0. So it is tau 1, you can do the math. It will turn out to be 9. So here actually, what you are, maybe I can walk only through the first one, which is alpha times T1, T0, which is 8 millisecond there, plus alpha 1 minus alpha, which is 0.5, times your predicted last value, which is tau 0, 10 milliseconds. So when you do the math, you will come with 9. So your first predicted estimate was 9. Your second predicted estimate is 12.5. Third is 16.24, 16.25, and the tau 4 is 13.125, right? So which is now your predicted value for the next burst, which is going to be executed. Now you can use this value to make the decision. So you will not have this value only for one process. You will have this value for all the processes which are ready at that time point for execution. So if this is the value, let's say for process A, you will also have the tau 4 value for process B, C, and D. Let's say you have only 4, and then you will compare tau 4 of all of them, and which one of them has the lowest tau 4, you will schedule that one for the execution. Okay. So the next CPU burst is estimated to be this one. After the burst is executed, it is measured as T4. So T4 will be the actual value which you can measure maybe by using some mechanism like how many clock cycles it took to complete. Okay. Any questions? No? Okay. So now let's say I make changes, small changes here. I have still the same time, bus time, like 10, 5, 15, and here I make changes. 2, 4, right? Now, if I draw the timeline again, so let's say I'm now first drawing the arrival, I'm putting these arrows to indicate the arrival time of the processes, right? So A is arriving at 0, B is arriving at 2, and C is arriving at 4. Now let's say again we use the same shortest job first algorithm, right? So at time 0, we have no other candidate, we have only A, right? Because B and 2, 4, B, C. Because B and C, they have not yet arrived, right? So we schedule, how long is it? 10, right? But here we have the B ready, right? So what options we have? Should we, the question arises is this, that since we are using the shortest job first algorithm, if we use that criteria, so what is the duration of B at time point 2? How long will it take? 5, right? And how much remaining time A has at this time point? It has executed for 2 time units and it still has 8 time remaining, right? Right? So now there are 2 options. One, we allow A to complete its execution for the burst time. And then after that, we make the scheduling decision here, right? Other option is that no, since we are saying that we are scheduling according to the shortest job, which one of them has the shortest execution time. So we make the decision here as soon as another process becomes available. And if it has smaller execution time or burst time as compared to the current one, what we do is that we do the preemption, right? So since we are making the decision according to the remaining time, shortest remaining time of the process, so this algorithm is actually a variant of what we have seen earlier, but it is now named as shortest remaining time algorithm. So you pick the job or pick the process which has now the shortest remaining time or remaining CPU burst. Okay. So at this time point, so what we have, if I like simply draw a table here, let's say A, B, C. At time 0, A has 10 time units to execute, right? It's bus time. Then at time 2, so these are not yet ready. At time 2, it has 8, and this one has 5, right? And this is yet not ready, correct? So what we can do is that instead of letting the process A to complete, we can preempt the process A and schedule the process B so it can execute, and then at time unit 4, it still has A to complete. It has 3 more units times to execute, and C is arrived and it is 15, right? So which one is still shortest? Right? So we will let it complete. So it can continue executing. So 2 plus 5, so it will complete at 7, right? So here you had A, you had B, and then At 7, it needs 8 more time units. This one is done, right? And it has 15. It needs 15 more time. It needs 15 time units to complete. So which one is smaller? Smallest? Yeah. So you schedule 7. You schedule 8. And how many more time units needs 8? 7 plus 8 is 15. Okay. And then at 15, this one is done, and only you have one candidate, which is C. So it will get completed at 30. Right? So this algorithm where what we are doing is that we are doing the scheduling based on the shortest remaining time. Okay, so we keep updating every time. If there is another process becomes ready, and it has the shorter time as compared to the currently scheduled process, we do the preemption. But while in the shortest job first, we will not do the preemption, so it is not a preemptive algorithm. But this one is preemptive. Okay, so if I asked you here, what is the waiting time, average waiting time for this schedule? So how you can find. So let's say first find the average waiting time of A. So this is the waiting time for A, right? Because it arrived at time 0, it was scheduled, and then it was preempted by B, and it had to wait this time period before it was scheduled again, and then it was completed here. So how long it waited? 7 minus 2, 5. What is the waiting time for B? It arrived at 2 and it got scheduled immediately, so it never had to wait, so 0. What is the waiting time for C? It arrived at 4 and it was scheduled at 15. So this is the waiting time, right? So 15 minus 4, 11. So average is 5 plus 0 plus 11 divided by 3. Okay. So this was waiting time. Now I'm rubbing this. What about finish time? At what time A, B, and C were completed? I think this is the easiest thing to do. So A got completed at 15. B got completed at 7. C got completed at 30. So the finish time is 15, 7, and 30. Right? And what is turnaround time? By the way, what is the definition of turnaround time? Yeah, go ahead.
It's the time from the process being in queue to the time that it's fully finished.
Yeah. So the time when the process becomes ready, or it is like submitted into the ready queue to the point where it completes the execution. Exactly same thing what you said. So if I want to get the turnaround time of A, so A became ready here, right? At 0, and it got completed here. So the turnaround time is for A is 15. And what is the turnaround time for B? B became ready at 2 and it completed here. So 7 minus 2, 5. And C became ready at 4. And it got completed at 30. So 30 minus 4, 26. So you can like sum and take the average turnaround time. So keep in mind that turnaround time is like the time point when it becomes ready and when it gets completed here. While waiting time is when a process becomes ready and when it is like not being executed. So like for example here, this is the waiting time for A. It was ready here, but here it is not scheduled. So we will count this time as A. But we will not count this time as waiting time for A because A is already complete. Okay. Any questions? Go ahead.
So where's this algorithm being run? Presumably it's a process that takes up core or needs to be run.
Suppose you are the scheduler. So in operating system, you are a module or you are a thread which is running itself, kernel thread, which is taking care of all these things, right? So you are also consuming a core, right? So actually you are also sharing, if there is a single core, you are also sharing resources with these processes which you are scheduling. Or if you have multiple cores, maybe you can run the scheduler on one core and these processes on the other. Any other questions? No? Okay. So this is shortest remaining time first, which we have already discussed. Or maybe I can simply read the slide to make sure there is nothing which I'm missing. So while a job A is running, if a new job B comes, whose length is shorter than the remaining time of job A, then B preempts A and B is started to run or execute. Okay. So here is another example. Let's say you have process P1, 2, 3, and 4. They arrive at time 0, 1, 2, and 3, like not at the same time, but at like different time. Arrival times are different. Bus time are 8, 4, 9, and 5. So what you do is exactly the same thing. At this time, there is no candidate, only P1 is the candidate. So you schedule it at one time point. What happens is that you find that, okay, there is another process waiting. Another process has become ready, so you need to make the comparison again. So what you compare is now it has executed for 8 time units, so remaining time units are 7. P2 has remaining 4, so 4 is smaller than 7, so you schedule the P2 and so on. Okay, you don't want me to walk again through the example, right? Okay, so average waiting time you can calculate as I have shown you on the board. Can somebody tell me what will be the implication of this one? I mean, in terms of overhead as compared to not doing the preemption? Okay. Anyone else? Okay, think about it first for a couple of seconds, 10, 5, 15 seconds. Think about it. When you compare the shortest remaining job first with the shortest job first, what is the overhead of this one? In both, I know in both we need to estimate the burst time, but other than that, yeah, go ahead.
Context switch every time the job is changed.
Job is we need to do the context switch every time also in terms of first when the job is changed, right?
Yeah, but
Or maybe you need to be little bit more clear. I know what you're going in the right direction, but try to be more clear.
so shortest job first, we wait until the job is finished. Whereas here we are preempting, so every time a preemption happens, we have to like.
So there will be more context switches as compared to the shortest job first, right?
Yeah.
Okay, so that is one thing. Anyone who can even address this more deeper, this question more deeper. That is correct. That is correct, but yeah, go ahead. Go ahead.
What's the question?
So we are trying to compare this one with the shortest job first, and in terms of overhead. So he said that one overhead will be that in shortest job first, you need to wait for the current job to complete, and then you make the decision. Here, when a current job is running and a process arrives, a new process becomes ready, you need to again do the comparison, and possibly there will be a context switch. So as a result, possibly you can end up in having more context switches. So the follow-up question could be like, how frequently I have to check if a new process has become ready or not? How do I know that here this process is becoming ready or true? Should I check after every one time unit? Should I check at every clock? Or what will be the implication if I check at every clock that if there is a new job becoming available, so checking a comparison at every clock will be like wasting more time, right? So like if you do the checking frequently, you are paying more overhead. But on the other hand, if you do the checking that whether a new process has become available already, if you're doing it less frequently, then what will happen is that your responsiveness is reducing. Why? Because maybe, let's say you say, okay, I checked at 0 and then I will check at 4. But in between, at time to time, unit 2, the process 2 was ready, right? So this process had to wait. So responsiveness has reduced, right? So there is like trade-off between more frequently or less frequently making the decisions. Okay. Any questions? Okay. Now we have covered two scheduling algorithms, right? One, shortest job first, another, which is variant of the same thing, but we schedule based on the shortest remaining time, and it is preemptive, while the shortest job first is not preemptive. Can you think of any other algorithm to schedule the processes? Spend like 10, 15 seconds. Try to think other than these two criteria, what we can do.
Do you do the longest job first?
I forgot to bring my phone today. So what is the time? 44. Okay, let's have a break. Let's have a break, and then we can continue. Okay. Maybe in the break you can think. Okay. So you guys are like in third year of your bachelor's, right? Third or fourth? Fourth. Okay, so you are like seniors? Okay. So how many of you are thinking of doing grad studies like master's, PhD? 1, 2, 3, 4, 5. Okay. How many of you have already started searching the positions like for master's, PhD? And NMSU out of NMSU? How many are thinking NMSU? 1, 2, 3, 4. Outside? Okay. Good. Good. So those of you who are thinking for grad studies, have you like, I know it is not possible to have a topic or a clear idea, but still you have some feeling that, okay, I want to do master's or PhD in this particular area. Not like exact topic, but an abstract idea like maybe operating system or databases or natural language processing or machine learning or whatever. So you raise the hand, right? Any idea?
Not much, it's maybe something with web, but.
Something with the web? Okay, you too? You raise the hand, right?
Yeah, also like either software or web.
Okay.
Maybe networks, that's pretty interesting.
Network?
Networking is pretty.
Okay.
Cool.
You guys?
Sure, but I was thinking something related to cybersecurity because I'm doing an internship related to that right now.
Okay. Anyone else? There, I saw some people raising hand there. So I think you are the one, right?
Yeah, I was looking like machine learning.
Machine learning. Anyone else?
If I do, it'll be web. I'm deciding yet.
Okay. Okay. No one in my area. I was trying to figure out like, is there anyone who is like potentially a candidate? No one. Okay. And I think it's not your fault. The reason is that we have some time, maybe we can spend 2-3 minutes. The reason is that in NMSU, I think you are required to take only one course which is related in some sense to hardware. I would not say architecture, but hardware. I think CS273. That is the only course, right? And other than that, you never get exposed to digital design, computer architecture, hardware security, trusted execution environment. So all these things are like very foreign to you. So I will never blame you. Yeah, okay.
think there's an architecture.
Yeah, there is, but as far as I know, it haven't been offered for so many years. I mean, if I'm not wrong. So, and since it is elective, so I don't know, I mean, how many people would be interested in taking that course. Yeah.
There's an electrical engineering and computer architecture course, but like this school won't cover financial aid and stuff because it's not a computer science elective.
Yes, and I mean, I was looking at the content of that CS273. To be honest, I mean, if someone wants to work in the or wants to understand the area of like computer architecture or hardware security, CS2 current content of CS273 is not appropriate for that purpose because you all of you have taken that course, right? So you are if I'm not wrong, you are understanding or you are talking about a specific AV or microcontroller, right? So which is like so everything you my understanding is that everything you have seen there is specific to that particular area. I'm not saying that those things are not applicable or those ideas or those concepts you discussed, they are not applicable to other microcontrollers or other architecture, but still tying an idea to one particular thing is not a good thing, first thing. And second, have you seen anything about sequential logic there? Sequential logic, combinational logic, timers.
Cover timers.
Yeah, I saw timers in the course content. Yeah. How to design adders, carry ahead. What is this? Look ahead adder. How to design multipliers. No, right? Processes pipeline. No. Yeah.
Are you thinking of teaching it all that is more focused on architecture?
In next semester, I am going to offer a course which is required for BS cybersecurity, that is hardware security. But after looking at the course catalog, I found that only CS273 is one which is related, and it is not designed in a way which is helpful for undertaking or for taking this hardware security course. So I will design hardware security course, but in a light version, in the sense that first I will try to cover those topics which are like ideally they should be like background prerequisite for taking the hardware security course. But since you haven't taken all the students have not taken it, so I will first cover the background and then on top of that build the hardware security ideas. And then if everything goes fine, maybe we need to update the content of CS273. And architecture course, my intention is to offer it not in next semester, but in a semester after that. Yeah. Okay. Now let's get back to the lecture. Okay. Okay. So yeah, the question I left on the table before the break was that is there an other algorithm criteria you can think of for scheduling the processes other than shortest job first and shortest remaining time first? Anyone else? Yeah, that is, I think, the most trivial one, or the like maybe the to me it is the one which is like first comes to your mind when you are like, so it is like first in first out or first come first out, like two alternative names for the same thing. Yes.
Not just waiting time first.
Yeah, that can be also a scheduling algorithm. So what we can do is, what is the motivation behind that, by the way?
I don't like waiting.
Yes, I don't like it. So if I am the one who is like, have been waiting for the longest time, I should be given the priority. Yeah. Okay. So Okay, now let's say we do the same example. We can keep everything same here. And if now we want to schedule, then who arrives first? A, then B, then C. So you will simply schedule in the same order. Like you schedule it for 10 time units. A. After that, B arrives, so it will be scheduled for 5 time units, completing in picture at 15. After that arrives C. You will schedule it 15 time units, 30. Okay. So the good thing about first come, first serve, or also known as FIFO, first in, first out, is that it is easy to implement. But what is the bad thing? Especially that now you have seen shortest job first or SRTF. So if now you compare first come, first serve with the other two, what is the downside here?
If you wanted to run a quick fork process before, if you needed to run a fork process before a long process, you actually put the long process first.
Yeah. In other words, what happened is that if let's say I have another process here, P4. Let's say I have another process, P4, which has execution time of, let's say, only time, two time units, and it became available at 1. So now it has to wait for P1 to complete and only then it can. So it means that it gets logged behind the longer process. And since this algorithm is not preemptive, like once you have scheduled a process, it will complete its bus time and then voluntarily you cannot like kick it out, just like in SRTF. In SRTF, we were like checking, is there another process becoming ready with a shorter time? So if that is the case, we preempt the current process. Here we can't do that. So now this will be like stuck behind the longer processes. One thing, and also since it is not preemptive, this algorithm is not as responsive as the preemptive algorithm. Okay. So now I can go back to the slides. So by the way, these couple of slides, it took me like 1.5 hours just to prepare these FCFS slides. That's why I decided, no, I am not preparing any more slides. I will just take as it is and use them. So here you have like process. The criteria is that the process that requests the CPU first, in other words, that becomes ready first, is given the CPU first, right? So let's say you have these processes, P1, P2, P3, 24, 33 as like their burst time, and you have the ready queue. So initially the ready queue is empty. So this symbol indicates that it is null, okay? Tail points to null, head is also null. So when the first process arrives, its PCB1 is like every process when it becomes ready, its PCB is inserted at the tail of the linked list. So actually it is first in, first out, or a FIFO implemented as a linked list. Okay. So every new process which becomes ready is inserted at the tail. And when you want to schedule a process, you pick the process from the head. Okay. So let's say you have, this is the initial state, and then your scheduler wants to schedule a process on the core. So process 1 is put on the core. It is removed from the linked list. And so this is like, it takes 24 time units to complete. After that, it is put it in the wait queue. Maybe after that, it will have an IO burst or something, but for the current burst, it is done. Okay. So maybe now it is waiting for an IO. And then after that, you get the next process from the head, put it on the core, and then it will take like 3 time units to complete. It will be finished at 27. Then you have only one process left in the ready queue. Let's say in the meantime, your PCB1, process 1, which was waiting for a IO, that IO is completed, let's say, and now it becomes ready again. So it is put again at the tail side of the linked list, not at the head. So you put it in the tail and waiting queue becomes empty. So once the process 2 is done, it is put in the waiting queue. And then after that, you again schedule the process 3. and it completes at 30, and so on. So in the same way, the algorithm continues as long as you have ready processes waiting in the ready queue, which is implemented as an ingest. Okay, so this is like showing you here the scheduling chart for the processes P1, P2, P3 completing consecutively at time 24, 27, and 30. Okay, so average waiting time is 70. Now, if we have again, let's say we have the same processes, but we have they arrive at a different order. Like P2 first becomes P2 becomes ready, then P3, then P1, but they have the burst time same. Now, since they are becoming ready in the order of P2, 3, and 1, we schedule them accordingly. We are using first come, first serve. So P2, P3, and P1. Now, if you calculate the average execution time, it is only 3 time units. Previously, it was, I guess, 17. Huge difference, right? So the difference is coming from the fact that in the previous case, the shorter processes were stuck behind the longer process. Here, shorter processes become ready earlier, and so they see lower waiting time. And as a result, also P1 also sees lower waiting time because their burst time is small. P2 and P3 are small burst time. Okay, this is known as convoy effect. Convoy effect basically the same thing where you have shorter processes stuck behind a longer process, and as a result, the overall waiting time increases. And this algorithm is not preemptive. Okay. So we have covered all this. Okay, here we have an example, and I want you to do it on your notebooks. Okay. So we have four processes, A, B, C, and D, arriving at time 0, 5, 10, and 15. We know the burst time for each one of them, 30, 20, 12, 10. Okay. What I want you to calculate that for all four processes, first use the first come, first serve algorithm and find the finish time for each process, at what time it completes each process. One thing. Second, the waiting time of each process using FCFS, first come, first serve, and turnaround time. Go ahead. Problem is clear, right? The statement is clear. Use FCFS, find finish time, waiting time, and turnaround time for all the four processes. Yeah, go ahead. Okay. Done. If you have solved and have the answers, you can raise your hand. Done. Okay, so let me do here for everyone, and then you can compare your answers with what I'm going to do. Okay. So we said we need to use the first come, first serve algorithm. So we have A becoming available at time 0, B becoming available at time 5, C becoming available at time 10, C and 15 becoming, D becoming available at 15. Okay. So we first schedule. So this actually gives us our order, right? So we start here and it takes 30. Let's say 30 here. It takes A. Then after that we have B, which is taking 20 time units, so it completes at 50. Then after that we have C, which is taking 12, so it completes at 62, right? And after that we have D, which is taking 10 time units, so it completes at 72, right? So finish time A, B, C, D, and A is 30, B is 50, C is 62, and 72. Waiting time. So A has 0, B became available at ready at 5 and was scheduled at 30, so 25. 30 minus 5, 25, right? C became ready at 10 and got scheduled at 50, right? So 40. And D became available at 15, ready at 15 and scheduled at 62, so 62 minus 15. 52 and 47, right? And turnaround time. So for A, submitted at 0, completed at 30, turnaround time is 30. For B, became ready at 5 and completed at 50. So 50 minus 5, 45, right? C became available at 10 and completed at 62, so 52. Ready at 15, completed at 72, so 62 minus 5, 57, right? And here you can calculate the average. Okay. Done? Same? Anyone who has a different answer? I think that I have done it wrong. Okay. Okay. So now I'm stopping here. What you can do is that you can repeat the same exercise using shortest job first algorithm and shortest remaining time job first algorithm. Okay. Any questions? Okay. Yeah.
What is average time?
What is what?
Average time is
average time, because when you have multiple processes running, so you need to look from the perspective of the whole system.
If I have process 1, 2, 3, 4, sequentially,
Yeah.
then again 1, 2, 3, 4. The average should be, I can start calculating from 3, 4, 1, 2, the average. Time will take where I yeah.
Time, actually, there are two things. One is turnaround time, and one is perspective of the singular process. So average waiting time for example is that if you have like the 10 processes, one of them may be taking like 10 times, but if average time is actually 4. So as a whole, each burden of average time is like 2. Yeah, but you right now, what the world is sorry for that.
Just need to verify.
Just give me 1 minute.